So I'm Phillip. I'm one of the maintainers in mixedmodels.jl, and so I, of course, have an interest in how we can visualize them. And so, of course, we can do things like traditional regression diagnostics. So we can do fitted versus observed. We can do fitted versus residual. You might notice that the data on this model are truncated, and you can see this nicely as this kind of sharp line. This is actually an important diagnostic. If you don't think your data are truncated and you have this type of line, you need to think again. And we can also do QQ plots. This is all implemented in mixed models Mach-E so that it's very easy to do. There's recipes. Now, if you're like me and my colleagues, you're screaming at this QQ plot because the aspect ratio is not 1. And so that's what you really want for QQ plots. But I was not going to bother getting that right for this because I want to focus on more interesting mixed models specific plots. So for example, we have what we call caterpillar plots. For those of you in the R tradition, these were often called dot plots in LME4 and its predecessor in LME. And these are the BLUPs, the best linear unbiased predictors, perhaps better known as conditional modes because it's not clear in what sense they're best or they're unbiased. And basically they're distributions of the offsets for each level of the group. So for example, you see on the horizontal axis, you have a particular individual. So we have, for example, subject 36 here, and it's sorted by the second column. We can actually specify mixed models Mach-E what column you want to sort it by. And you can kind of see whether or not there's a correlation pattern here. In this particular model, there's not really, but in some models, you'll see a stronger correlation pattern. And you can kind of see how these different offsets vary between participants. You can also do this as a QQ type plot for these unbiased estimates. But I want to spend a little bit more time on a different type of plot, which we call a shrinkage plot. And this is an example from a slightly simpler model. The axes are the different variance components in a mixed model. So here we have the by-participant intercepts on the x-axis and a by-participant slope on the y-axis. The red dots are approximately what you get from an ordinary least squares fit within participants, approximately because that's not actually how we do that. And the blue dots are the conditional modes, so the BLUPs. And what you can see is what a mixed model actually does compared to classical regression. So you have this notion of shrinkage, this regularization, where the individual data points are moved towards the population level estimates. And this is actually a good thing. Regularization in regression is a good thing. You might be thinking, okay, but is there more structure to this? And also, I'm claiming that they're being shrunk towards the population mean, but if you look, some of these points seem to get more outward on a certain axis. So for example, this participant here on the left might look like it's going out a little bit further. And so is there a better way we can visualize this? And the answer is yes. We can add in these correlation ellipses. So these are also curves of equal probability. And this is computed from the covariance structure of the mixed model. And so what you can actually see is that the points do move inward within a correlation ellipse. They move further inward. So they are actually getting into a better position. We can also use this type of plot to visualize excess dimensionality, so singular fits in mixed effects models. What you can see is that for this more complicated model, so we have all the pairs, that's why we have all the pairs, that for some of the variance components, things collapse down into a line. And this is actually indicative that this model is overly complex. And because of the regularization, we can actually fit these overly complex models. But this also hints that our models are more complicated than they need to be. There's a big debate in the mixed models literature about how you should specify these things. And the answer is, from my perspective, is this is being collapsed down to one dimension. It's singular, so you don't actually need that dimension. And you can see for some things, it's actually collapsed down to a point. And you can also see the effect, for example, of constrained covariance structure. So in this case, we've constrained the covariance structure to be orthogonal, so to not have zero correlation between these things, so that the covariance matrix is diagonal. And you can see that the shrinkage can only occur along perpendicular lines. And this is otherwise the same model as the previous plot. And you can actually see what constraining the covariance structure does to our ability to have efficient shrinkage. For example, in this panel, how that shrinkage looks compared to this panel. And so you can see that this constraint in the covariance structure, while it makes it easier to fit a model faster, actually really does have big impacts on what our estimates are. And finally, as I fly through my slides faster than I thought I was going to, I also want to highlight something that we took advantage of with Mach-E. And for mixedmodels.jl, we use a very nice profiled log likelihood to be able to evaluate these things very quickly and fit our models very quickly. And we use the Bobby-Quill optimizer from NLOpt to do this. And the likelihood in a mixed model is quadratic, or in a linear mixed effects model is quadratic. And it turns out that Bobby-Quill, which stands for bounded optimization by quadratic approximation, is very good at solving quadratic problems. And so on the bottom here, we have the different parameter values as the optimizer explores the parameter space. On the top, we have the objective, so deviance. And you can see that there's this initial broad exploration of the parameter space, and then the optimizer jumps to near the optimum. And it's nearly perfectly at the optimum. I want to leave time for one question at least, so I'm going to fast forward this recording. And you can see that actually the optimum or the log likelihood doesn't really change later, even though this one parameter value shifts a little bit. And this actually suggests something that we've implemented in a recent release, which is that you can reduce the convergence criterion when you're doing things like the parametric bootstrap, because it's better to have more replicates that are slightly worse than to have very few replicates that are exceptionally high quality. And that's it from me. I'm happy to take any questions. If not, then the next speaker has more time to set up their laptop. So I'm sure they'll appreciate that.
You also have time to think of questions.
Okay. Feel free to file issues on Mixed Models Machis. Pop me a question on Slack or Zulip. We're always happy to have this out there. And for those of you who really care about the stats behind this, a longer, more detailed, and slower spoken version of this presentation will be presented at the joint statistical meetings in 2 weeks. Thank you.
Let's thank the speaker again.